Welcome to EDU World Space.
Problem 7.71, we have a block with a mass of 50 grams sliding around a circular track without friction, which has a radius of 0.8 meters. Now we're told that the normal force at the bottom is equal to 3.4 newtons, and we'd like to find the normal force at the top. So let's call the bottom point A, let's call the top point B. So we're going to combine what we know about Newton's second law and circular motion with conservation of energy. So the sum of the forces is going to equal the centripetal force, preferably not going off the top of the page, and then, well, and then because doing work on the block is gravity, which is conservative, the total mechanical energy will be conserved. The normal force is perpendicular to the direction of motion, and so it does no work. KA plus UA equals KA plus, KB plus UB. So, at the bottom of the circle, so the sum of forces is the normal force at A minus the weight of the block, and this has to be equal to our centripetal acceleration, or force. This part is the acceleration, and multiplying it by the mass makes it the force. So the speed at A is 6.82 meters per second. So now we can use the conservation of energy to find the speed at point B, because now we know how much mechanical energy there is. So if we call this point if we set B to be A, if we set A to be our 0 point for measuring gravitational potential energy, we just have the kinetic energy at point A, so 1/2 mva squared is equal to 1/2 mv squared plus mg times 2r, because it's the radius, so you go, the diameter, you're one diameter above where you started, which is twice the radius. So now VB, doing the, just subtract this off, multiply it by 2 over m, take the square root, and you find that it's going at 3.89 meters per second at point B. And so now we go back to Newton's second law here with what we know about circular motion. So the normal force at B, which we're wanting to find, plus the weight is equal to m dp squared over r. So the normal force is equal to the mass times the centripetal acceleration minus the acceleration from gravity. And then this works out to be 0.456 newtons, which we can see is a fair bit less than at the bottom because it's lost speed, and also gravity is now pulling it inwards instead of outwards, and so the normal force doesn't have to be as high to counteract that if it's keeping the block in the track.